Welcome to lecture 24 on risk management and insurance. The last lecture we finished with equation 36, which summarized everything that we have done in that lecture. Remember, at time big T, when the insurance company is dissolved, so we look now at time big T, when the insurance company is dissolved, then both shareholders and insurance buyers have a claim on the assets of the insurance company. And this equation here shows actually shows what those claims are. The shareholders, their claim can be represented by a call option. That's the notation of a call option. The insurance buyers, they naturally are entitled to the insurance payouts for the losses, and then that's adjusted by a put option. So the insurance buyers do not just get the losses covered, it's actually it's somewhat reduced by this put option, by the value of this put option, which measures the risk that the insurance company will go bankrupt. The insurance buyers write that option because they assume the loss, that they absorb the loss that arises when the insurance company goes broke. The shareholders just walk away with zero. They walk away with nothing, but the insurance buyers really lose something when the insurance company gets broke. They will no longer be completely compensated for their losses. So they will no longer completely be compensated for this year. Now let's see whether this equation makes sense. Let's first look at the situation where the insurance company is solvent at time big T. So the assets are bigger than the liabilities at time big T when the insurance company ceases operations. Now, when assets are bigger than liabilities in this call option, that's a positive number, A bigger than L. And so AT minus LT applies, and not the zero. Now, when assets are bigger than liabilities, then here in the put option, we have a negative figure. Assets bigger than liabilities. That's negative, but we look for the maximum. So here's a zero applies. So what we have here is then minus LT plus LT, that drops out. Anyway, this here will be the zero. And so we just have here the AT, and that's the AT here on the left side. So the equation makes sense when the insurance company is solvent. We can do the same exercise when the insurance company is broke. Let's also do that. So let's now assume the insurance company is broke at time big T. So the assets do no longer cover all the liabilities. The assets are less than the liabilities. If the assets are less than the liabilities, the insurance company is broke, then AT minus LT in the call option at the beginning becomes a negative figure. So that's now negative. So here's a zero applies because AT minus LT gives me negative. And here, AT is smaller than LT, so that's a positive number, that's bigger than 0, so that's bigger than this 0 here. So the LT minus AT applies, because that's now positive. So what we have in the situation of a insurance company that's broke, so LT cancels out with this LT. And then I have here a minus AT, but I have another minus here. So I have minus AT, and in the end, I have here AT. It's actually pretty neat. You have to think this through again. This equation 36 really summarizes about everything we have done in the last lecture, and it makes sense. The equation certainly holds in both situations, whether the insurance company is broke or whether the insurance company is solvent. We will get actually, we will get AT here on the left side. The equation, we will get this AT here. The equation holds. But more basically, this equation just simply shows the entitlement of the shareholders and of the insurance buyers at time big T when the insurance company is dissolved. And the entitlement of the shareholders is represented by a call option, and the entitlement of the insurance buyers has two parts. Naturally, they are entitled to the insurance payouts, but then that's actually adjusted by this put option. They wrote this put option because they assume the losses when the insurance company gets broke. The shareholders don't assume those losses. The shareholders just walk away with 0. Now we can use the Black-Scholes option pricing model to value those call options and put option here. So let's assume C stands for the value of the call option and P stands for the value of the put option. So I just put in C and P, and C and P is calculated using the Black-Scholes model. We will see this actually in the next chapter, how that's done. Also, let's now shift the timing from the time when the insurance company is dissolved. Let's shift it to time small t at the beginning, when the insurance company starts operation. So we look at the assets at the beginning, and so those liabilities here, which are paid out at the end for the insurance payouts, we have to discount them. So that's a discount factor. We just discount it here in continuous time using the Euler number. Up here I have a negative interest rate. As the interest rate, I have a minus sign, and so that's discounting. So I'm shifting from A big T, I'm shifting to A small t, but in the book by Zweifel and Eisen, they don't write the small t here, so I also don't do it. But by shifting, I have then actually to discount the values of time big T. I must discount that one. And the call options and the put options, anyway, those Black-Scholes prices apply to time small t. So everything is now looked at here from the point of view from the beginning when we establish the insurance company. Now, equation 77 determines the optimal financial structure of a firm. here an insurance company, but it can also be applied to other firms. So I have the assets, the total investment portfolio. That's A here. At the beginning, at time small t. So it's applying here to time small t. And that's equal to the capital, to the equity capital, and the discounted payouts, insurance payouts, adjusted for the insolvency put. So that's what I have here. So A is equal C plus the insurance payouts discounted, adjusted for the insolvency put. So I can, the balance sheet, I represent actually an equation. Balance sheets are just simply equations. You see the left side should be equal to the right side. So in accounting, you don't write equations, you do balance sheets or you do T accounts, but those T accounts are just simply equations. And here I have the equation, but this equation, actually I can now write down the balance sheet. The assets equals the liabilities here and the equity capital. So the equity capital represents the entitlement of the shareholders, and the debt, this here, okay, represents the entitlement of the insurance buyers. They are entitled to the insurance payouts adjusted for the insolvency put. Now the insurance buyers are entitled to the assets to this amount because they paid the premium income. They paid the premium to the insurance company. From the point of view of the insurance company, that's a premium income. This equation you may use as an arbitrage condition. If actually we have this inequality, the insurance premium is bigger than what the insurance buyers are entitled to. Yeah, okay, that's bad business, and so they will not buy insurance. And the insurance company must reduce the premium. And similarly, if it's too small, then the insurance holders are entitled to more than what they paid for, and naturally the insurance company will notice that, and it will increase the premium. So here we have this equality. The insurance premium is just simply equal to that here. So insurance buyers are entitled to this because they paid the insurance premium. Now we can also divide by capital, and what we get here is the old leverage ratio that we discussed before. Now in the insurance capital asset pricing model, we use the actual letter K for capital. Now here we use a C because the equity capital can be represented by a call option. But this is just simply the leverage ratio. So optimal leverage ratio is the amount of premium income here relative to the equity capital. Or this here, the entitlement of the insurance buyers, the debt of the insurance company, the liability of the insurance company to the insurance buyers relative to the capital. So an insurance company that works with a small amount of capital has actually a high leverage ratio. It has a lot of liabilities here relative to capital. Now you can also rearrange equation 37. Then you get equation 40. You're simply rearranging So rearrange brings a C on one side. So we have the C here, we have rearranged, and that's what you call the put-call parity condition. It's a very famous equation. It gives you a relationship between the call option price and the put option price on an asset. And this put-call parity condition is commonly used to determine the optimal financial structure of a firm. By this I mean it's commonly used to calculate how much debts should a firm have relative to equity capital. So that's the financial structure of the firm. How should you finance a firm? Should you finance it through debt, or should you finance it through equity capital? The equity capital is owned by the shareholders, and here actually the debt is owned then by the insurance buyers. That's a liability towards the insurance buyers. So how should we finance this company? The equation shows it. This put-call parity condition shows it. It's a very well-known equation in finance. It's in all finance textbooks. And Cummings starts the derivation of the option pricing model with the put-call parity condition. So he goes the other way around. He writes first down equation 14, because everybody knows it, and then out of this, he explains the option pricing model of insurance. We did the other way around. We started with the option pricing model, and in the end, we had the put-call parity condition. So we just did it the other way around. So the premium income is given by equation 38, this arbitrage condition. So equation 38 determines the optimal premium income, which entitles then the insurance buyer to the assets. And you can now use so insolvency. You can use the put-call parity condition from before to calculate the value of this put, and then you can calculate the optimal premium income. So there is no need here to know the distribution of the losses as we had it in the ruin theory. It's not so easy to estimate the loss distribution, but here we don't use it. We also don't need the underwriting beta as in the capital asset pricing model of insurance. Now here, everything is just done by the option market. The only thing you have to observe is actually here the price of this insolvency put, and then directly you can calculate the optimal premium income. So there's no need to estimate loss distributions. So there is no need to estimate underwriting betas as we did this in the capital asset pricing model. The only thing you need those option prices. And these put option prices, you can then actually even then derive it here from the put-call parity condition here from the call option price. Also, we have this equation 41 here. The premium income is just A minus C, but they don't use this equation in the book. What is the empirical evidence for this? In the next table, I show you the underwriting returns. Remember, the underwriting returns are, it's a percentage. So it's the premium income minus the losses, including the administration costs, divided by the premium income. And the premium income is actually total premium income. It also includes the safety loading. So total premium income minus total costs divided by premium income, that's the underwriting return. We used this before. And here you have the actual figures. It's for the United States over a time period of 60 years. this research has mostly been done in the 1980s and 90s. So we have here 60 years of data, and you see the average underwriting return is 1.3%. It's positive, but small. It has a big standard deviation here. So in many years, it will have been negative. But we discussed it's no problem if the underwriting return is negative, if the underwriting business is a good hedge for the assets of the insurance company. That's what we discussed in last lecture. Now, the capital asset pricing model predicts for those 60 years an average underwriting return of -1%. So it actually predicts a negative return. That's because underwriting is a good hedge for the insurance company for its assets. So it's even willing to work with a negative underwriting return. It does not abandon the underwriting business because the underwriting business serves as a hedge. But it's also a big standard deviation. So those two figures are not, statistically, they are not really different if you do a test. So option pricing model predicts an underwriting return of 1.32%. So it actually just hits the actual observed figure. So it does very well here. But again, with a large standard deviation. Now, the insurance commissioners, they made the same mistake as the Germans. They actually proposed higher returns, higher underwriting returns, 4.7%, much too high. It's a very small standard deviation. But that stuff is wrong. This would explain, we have seen this in Germany, 4%, then implied, or 3% in Germany implied a very high return on the capital of an unrealistically high return on the capital of the insurance company. Because with 4% underwriting return on top of it, it's a good hedge. So it's really too good a deal, this underwriting for the insurance company. So they made the same mistakes here as the Germans. In Massachusetts, they were better. They actually, had here on each year, they had an average underwriting return sort of slightly negative, which corresponds roughly to the capital asset pricing model. So here we have the actual figures, and then here we have the two figures from the capital asset pricing model and from option pricing model. And then here we have some rules which were given by regulators, by the government, and here they made the same mistake as in Germany. It's American figures here. Now, during the global financial crisis, financial markets became more volatile, so the sigma A increased. Remember what the sigma A is. Here, it's actually a scaling factor for the standard deviation of the stochastic process of the assets. So we have here this Wiener process, but here we have a standard deviation of 1, and then you multiply by sigma A, that scales the standard deviation. So if this sigma A is bigger, then we have here bigger shocks. And so we get here bigger changes in the asset price. Typically during the financial crisis, this standard deviation will increase. This parameter is not really fixed. So sigma A increased, markets become more volatile, which means the value of an insolvency put increased. The value of an insolvency put increased. When markets are more volatile, then you're happy to have a put option, it gives you the right to sell. And you still can actually sell at a higher price, maybe when the markets have fallen because they are volatile. So the value of insolvency puts, it makes sense. The value of insolvency puts increases when the markets are more volatile, and also when actually the solvency of the insurance company falls, then it's more likely that they will default, and so the value of the insolvency put increases. So the insolvency put increases, it's negative. So the premium income, the optimal premium income of the insurance company falls. So insurance companies will do less business. They will do less financial intermediation. And so the financial markets will become less efficient. Naturally, also the banks will shrink the balance sheets. They also will do less financial intermediation. So during a financial crisis, naturally, the financial markets become less efficient. And that now also applies during the coronavirus crisis. I would expect the financial crisis now, during the crisis, the financial markets to become less efficient. And then we have less financial intermediation. It's harder to borrow money, and that will hurt the economy. And investors an investor will have more difficulty to find a lender, and will probably have to pay higher interest rates and so on. Okay, that was today's lecture. Thank you.